脑人言，
各位脑人言的观众们，大家好，我是薛晨，欢迎大家来参加本期的脑人言。今天我们是Neureport 科普报告的第89期，今天我们请到了明尼苏达大学的刘世照博士，刘博士先给观众打个招呼，
大家好，我是刘世章。
好，刘博士不久前刚刚从Rochester 大学毕业，他研究的是这个大脑的信息处理和学习的机制。那么他的博士论文的一部分呢，最近也是在 Science 上发表了。所以我之所以邀请他今天来讲这个工作呢，是因为我觉得他提供了一个非常好的看问题的角度啊，就是因为我们大家都知道，这个大脑的神经元活动非常的贵，因为它这些我们就大脑里面的这些 spikes，它消耗了人体大约20%的能量。所以，当我们学习一个任务啊，然后做得越来越好，行为上面做得越来越好的时候，直觉上应当是说，就是大脑应该学会了怎么样去高效的使用这些能量来处理信息嘛，对吧？那这些冗余应该减少，对吧？但是有意思的是，这篇工作就偏偏告诉我们说，这个冗余反而是增加的。那么就是今天就刘博士会告诉我们为什么。嗯，那么给这个今天如果是第一次听我们节目的观众朋友们，稍微介绍一下，就是我们节目形式呢，就是一开始会有一个这个45分钟左右的报告，是录屏加直播的。那录屏的内容之后会放到各大平台上面。那么就是在这个报告结束之后呢，我们也会有一个45分钟左右的这个问答环节。那这个环节是直播但不录屏那么所以大家可以就是在报告结束之后，然后再和我们交流。那么尤其是今天，因为这个刘博士他告诉我说，他其实还有很多更有意思的工作，很多结果没有发表。那么就是不太方便录屏，所以说我们会在这个问答环节继续去探讨一些这些更有意思的工作啊。所以我感觉就是这个刘博士确实挺厉害啊，就是发表一篇 Science，感觉只用了他50%的功力啊。所以那我就不多说废话了，那时间交给刘博士。
好，谢谢薛前辈，然后非常详细，然后非常吸引人的介绍。然后呢，我 share 我的屏幕，OK，等一下哦。呃，大家可以看得见我的 slides 对吧？
可以看见。
对，然后我的就是报告会用英文，然后主要是因为我之前都是用英文做的 PPT，然后稿子，然后大家中途问问题的话，就是用中文问就好了，然后我就可能会中英夹杂地去回答然后就是如果有什么 clarification 问题的话，就是随时打断我问就好。OK。Okay, so I want to start with these two cat images. So now who thinks they're the same cat in different position and who thinks they are two different cats? So actually, these are my two cats, Bib and Bob. They're brothers and look very similar. So when my friends first meet them, they really say, I can't see any differences. They just look the same. Then I would explain that Bob's nose is orange and Bib has more white on his nose. And Bob's really slim, but Bib is more chunky. And Bob has lighter fur, but Bib has darker fur. And some of my friends might say, now I can vaguely see some differences after it told me. But for me, I can easily tell which cat it is from just one look, even from a distance or even without eyeglasses. And I don't simply know the differences, I really see the differences. So my visual perception for these cats has dramatically changed. And clearly, there's some prior knowledge or even long-term learning involved in this situation. But the question is, how does information processing in the visual system support this? The visual system is hierarchical and has many brain areas. There are feed-forward, feedback, and recurrent connections between these areas. To study visual perception, we need to understand the information flow in this complex system. And one critical question is, what are the roles of the feedback connections? What kind of signals do they carry, and how do these signals modulate information representation? And the visual information is represented and communicated by the spiking activity of visual neurons, which are very noisy. Even when we keep the input image the same, the response of neurons are variable. Very often, these variabilities are correlated among neurons, and has been long suggested that the correlated variability can have a large impact on the information in the neuron population. So one way to understand this complex stochastic system is to figure out its computational goal. Vision has been conceptualized as an inference process because the brain does not have direct access to the outside world, and the only observation it has is projections on the retina. The visual system needs to make inference about the latent cause of the observation, and we perceived the most probable cause of the image. Currently, there are two fundamental different frameworks on visual processing in terms of computational goal and what type of inference it performs. The more classical discriminative inference framework focuses on direct transformation from retinal input to task-relevant representations. In contrast, the generative inference framework proposed that the visual system builds a generative model that captures the causal structure of the world and inverts this model to make inferences for perception. So these are three fundamental questions in visual neuroscience, and as I will explain next, they are closely interrelated. In particular, these two frameworks have distinct views on the role of feedback signals and the variability of neural response. So in the framework of discriminative inference, the computational goal of visual system is to directly extract task-relevant variables. The mapping between observation on retina and posterior over latent variable can be approximated by deep neural network. In fact, this framework underlies most artificial models of vision. In this framework, posterior beliefs are only represented at the very top level, and the intermediate layers only represent likelihood. Discriminative inference itself does not need feedback, but to explain the existence of feedback signals in the brain, it proposed that the main function of the feedback is to improve representation of the task-relevant variable, either by sharpening the tuning curve or reducing harmful noise. Also, it treats variability in the neural response as meaningless noise, mostly from feed-forward or recurrent pathway, which should be minimized to improve representation and coding efficiency. On the other hand, the generative inference framework proposed that the visual system builds a probabilistic generative model of the visual world, which reflects the causal structure of how the observation is generated, and then it inverts this model to make inferences about latent variables. In this framework, sensory neurons at all levels represent posterior belief about some latent variable, and it follows the Bayes rule and combines prior and likelihood. The variables represented in each layer are different, and one critical role of the feedback connection is to communicate prior or belief signals. Because the prior itself is also stochastic, this would introduce additional variability in the neural activity from the feedback source. So it implies that the response variability is not just meaningless noise, but reflect variability in the posterior beliefs. So to summarize, these two frameworks have different interpretations about feedback connections and variability in your response, and how the feedback connection modulates response variability. And in this project, we aim to directly resolve this debate by leveraging these conditions and eventually by leveraging these distinctions, and then eventually provided evidence for the generative Bayesian inference. So we focused on information redundancy, which is closely linked to the correlative variability and its impact on population information. So next, I'll explain how exactly it was defined. Also, why increase of redundancy is supportive evidence for generative Bayesian inference. So in our experiment, we had awake animals performing a perceptual decision-making task. In this case, they look at gratings and try to report whether the average orientation is 0 or 90 degrees. While they perform the task, we record spiking activity of populations of neurons from wave 4 with Utah array. So here are some example spiking activity of one neuron to one orientation. Each row is one trial, and we show the same stimulus for many trials. And here is this neuron's response to 90-degree orientation and spiking activity of second neuron in response to this stimuli. So we can count how many spikes each neuron generate during each trial and plot the spike counts of each neuron against each other in this two-dimensional space. So this dot indicate spike counts of two neurons for one example of 90-degree trial. We can do this for multiple trials, and then across trials, compute the mean and the covariance, and then do the same thing for the 0-degree trials. So if we connect the mean spike counts of these two classes, we get the tuning axis for this task. In this case, both neurons prefer 0 degree, so the tuning axis points to the upper right. So by information here, I specifically refer to linear feature information about the task relevant variable, and in this case, orientation. So intuitively, it captures how well we can decode a linear decoder can decode orientation category from the population neuron response. The formal definition of linear feature information in these neurons is the product of the derivative of the tuning curve divided by the covariance. So you can see it doesn't only depend on the strength of orientation tuning, but also the magnitude and structure of the covariance. In this example, the correlative variability is positive and aligns with the task tuning axis, creating more overlap between the two classes, and this would reduce the information about the orientation category. Okay. And now we can look at many more neurons and compute linear feature information from them. So if we ignore the correlation in the response variability and assume all the neurons are independent, we get the so-called shuffled information. So this I shuffle is equivalent to the sum of individual neurons' information, so it should grow linearly with number of neurons. And the term shuffle comes from that we can destroy the correlation by actually shuffling the order of the trials. But in this work, to compute I shuffle, we just made all the off-diagonal elements of the covariance matrix at 0. But when we take into account the covariance matrix, the covariance, and compute the real feature information, it only grows sublinearly. And the gap between the shuffled and real feature information is defined as information redundancy. It captures the difference between how much information this neuron could represent if they're all independent and how much they actually represent. So the reason why there's such a positive difference must be that some of the information is shared between neurons, which means that part of information is redundant. On the other hand, if neurons are independent from each other, the information redundancy would be 0. So I want to clarify that this is real data and it's not strictly 0, but in theory, it should be 0 in the independent case. So our question is, if the monkey needs to learn this task, which is to discriminate and report the orientation of the stimuli, how would information redundancy change over task learning? In the framework of discriminative inference, learning should make population coding more efficient. And one way to achieve that is by making neurons more independent and reducing information redundancy. On the other hand, the generative inference framework predicts the opposite. Information redundancy should increase with task learning. But why should it increase? So in our generative Bayesian model, sensory neurons represent posterior belief about the latent variables by combining input likelihood and prior beliefs. This prior signal is shared among neurons. Because it's the same signal sent to multiple neurons, it will introduce correlative variability and redundancy among these neurons. And with task learning, the prior belief about the task will get stronger, so information redundancy will also get stronger. Another way to think about this increased redundancy between neurons is by thinking about the redundancy in the image itself. So the stimuli has a consistent orientation such that the orientation in one part of the image is predictive about orientation in another part of the image. So let's say we have two neurons that respond to these two parts of the image, and now the activity of one neuron is predictive or contains information about the activity of the other neuron. So by task learning, the brain picks up this statistical structure, and as a result, the activity of each neuron is not only informed by the image in the receptive field, but also by other neurons. And this would introduce redundancy within the activity of these neurons. So the rationale behind this project is that
I'm
we
sorry to
focus, yeah,
interrupt. Can I go back to the previous slide, the one before this?
sure.
Um, the one before this. Yeah,
The model or even before?
before this.
Okay, here.
So yeah, I understand the intuition, the intuitive illustration you had for um, reduced redundancy and reduced correlation. So is this, I just want to confirm, is it when you talk about reduced redundancy, effectively what happens in on the illustrations on the left, is it always reduced correlation or can it be something different?
Um, so I guess in our definition of redundancy, it is closely linked to correlation. So if it's independent, it must be like zero redundancy, right?
Okay.
But I'm just thinking whether maybe it can be like still the overall correlation is consistent, but redundancy is reduced. I think maybe that's also possible.
Uh, okay.
It really it depends on the structure also structure's correlation and how that aligns with the task tuning.
Yeah, sure. But
Yeah.
in a two AFC task like this, it's
Mhm.
essentially the same, isn't that so?
Well,
Reduced redundancy and
so if you think about like neurons that have opposite tuning preference, then
all right, yeah.
yeah,
Okay,
yeah, right.
thanks.
Yeah, so it's more so redundancy is more equivalent to like information limiting correlation, but not average correlation.
Sure.
Yeah. Okay. So the rationale behind this project is that we focused on a key difference between these two frameworks, which is whether sensory neurons represent posterior by incorporating prior beliefs from the feedback. And to test this, we can manipulate the prior and look at how the activity of sensory neurons is modulated. And experimentally, we can track activity over task learning because learning is expected to enhance prior belief about the task. Or we can change the task context. In that case, to better perform the task, the subject also needs to adapt their task belief to the context. And if sensory neurons represent posterior, prior would introduce shared variability and information redundancy. And when the prior signal becomes stronger, information redundancy would also become stronger. And such results would support generative inference. Otherwise, if we see a redundancy reduction or no change, then it would support discriminative inference. So next, I'll show you our empirical results about increase of redundancy on three different time scales. Over task learning for many weeks, within task trial of less than 2 seconds, and during task switching within experiment session. So we trained two macaque monkeys on two orientation discrimination tasks. The oblique task is to discriminate between 0 and 90 degrees, and the cardinal task was between 0 and 90 degrees, and the oblique task was between 45 and 135. Each trial, we first showed two choice targets, and then the stimulus for 1.6 seconds. And after stimulus offset, the animal needs to report the decision about orientation by making a saccade to one of the choice targets. And the mapping between orientations and targets for each animal are shown on the top. So the layout and luminance are different for each task. So here are some examples of our stimuli. And these are some images from easy trials from which you can see some of these four orientations. But animals mostly worked with this ambiguous stimuli. But because they were very well trained, their accuracy on these stimuli were also above chance level. In the experiment, we first gave the animal some training on one task, and then we did a surgery to implant Utah array to V4 and recorded population activity while the animal kept learning on the first task. And after the animal's performance plateaued, we switched to the other task and recorded the whole learning process. And then we did the same thing for the other animal, but counterbalanced task training order. So this is animal's performance after learning. And for monkey R, we see the psychometric curves are pretty good, although performance is lower for the oblique task. And it's also the case for the other animal, monkey G. So we really try to improve his performance on the oblique task, but this is what we eventually got. So we also want to know the animal's strategy. And to do that, we run logistic regression to predict the animal's choice from orientation energy in the stimulus. And the regression weights gives us psychometric kernels. There are two components of these kernels. One is temporal kernel, which tells us how much each image frame influenced the animal's choice. So for example, this is the temporal kernel of monkey R cardinal task. So there's very strong primacy effect, meaning he primarily used the early evidence to make decisions. And this is also true for oblique task for this animal. And for monkey G, we also see primacy effect, although these kernels are not as deep as monkey R's. And the second component is orientation kernel, which tells us how the animal uses the orientation information. So for example, as shown by this red dashed line, for the cardinal task, an ideal observer would have a peak at 0 degree and a trough at 90 degree. And for the oblique task, the ideal orientation kernel should be shifted by 45 degrees. And the solid lines are empirical orientation kernels we estimated from the animal's behavior. For monkey R, although there's some noise, but it roughly aligns with the ideal ones. For monkey G, it aligns really well for the cardinal task. But for the oblique, the peak at 45 is missing, and we have a good trough at 135 degrees. So to track the animal's performance over training, we defined learning index. So the reason why we did not simply use the accuracy is because the difficulty levels also changed throughout learning. So intuitively, the learning index is a combination between how much the animal uses the stimulus orientation and how well their orientation strategy aligns with the ideal strategy. So this figure shows the time course of learning index. Each data point is one session, and typically the interval between sessions is 1 day, but sometimes there's weekend or longer breaks in between. So you can see for the cardinal epoch of monkey R, learning index increased and then plateaued, but with some fluctuation at the end. And we see very similar trend for the oblique task. Here you can see that this abrupt drop is because we tried running one oblique session just for comparison, but that really confused the animal. And for monkey G oblique epoch, it plateaued at relatively low values. But his cardinal performance was very good and kept improving with training. So for each session of data, we compute the linear facial information of the population of neurons. So let's first look at facial information of this one example session. So the shuffled information linearly increases with the number of neurons, while the real facial information grows sublinearly. And this gap, the information redundancy, is very big in this session. And here's another session with very low redundancy. And the question is, which one is before and which one is after learning? From the perspective of discriminative inference, which underlies how people traditionally think about a visual system, learning should reduce information redundancy. But it turns out the opposite. The top session is actually the very last session, and the bottom one is very early on. So here you see the evolution of redundancy over time in this epoch. Clearly, it increased with learning. Now let's look at all the 4 epochs. This epoch I just showed you, and in monkey R, we see the same result. Information redundancy increased with learning. But here's an outlier. In monkey G oblique, redundancy first increased and then dropped to almost 0. But when we directly quantify the relationship between information redundancy and behavioral performance, we saw significant, very strong correlation in all of them, including this outlier epoch. So this positive relationship between behavioral performance and redundancy is consistent with the prediction of generative Bayesian inference. So given that this is a pretty surprising result from the classical perspective, I just want to emphasize that we made a lot of efforts to try to make sure this is not driven by any confounds, including eye movements. But it's hard to imagine the actual facial information decreased with learning as behavioral performance improved. But when people think about redundancy is harmful for the real facial information, like in this scenario, there's actually an implicit assumption, which is information in each neuron, meaning the shuffle information is fixed. But there's another possibility, which is that the population information does not change, while the information in each individual neuron increase, or it could be a combination between these 2 scenarios. So to understand what's going on, we first analyze some synthetic data from a generative Bayesian model. This data set has 3 sessions, and each one corresponds to a learning stage. As expected, the information redundancy in our synthetic data increased with learning. But it's not driven by any decrease of the real facial information, and in fact, it increased a little bit. But the shuffled facial information grows much faster than the real one, leading to higher redundancy. So what we think what's going on is that it's an information redistribution process. So decision-making area incorporate information from all sensory neurons to form a task belief, and then propagates back this belief to these neurons. In this process, each neuron gets more information from all the other neurons. Since the eye shuffle is basically a sum of individual neurons' information, it will increase. But this seemingly extra information is just replicated copies from each other, so it's redundant. But how come the real facial information increase at all? Because computation should not create any new information. So actually here, to simulate a real experiment where we can never observe all the task-relevant neurons, we use subsample from the whole population. So we first confirm that the real facial information in the whole population activity of this model actually decreased. But as we sample a smaller subset of neurons, the increase of real facial information becomes more salient. So the way to interpret this is that information redistribution does not only happen within individual neurons that we observe, but also from the unobserved neurons to the sampled population. So next, let's look at the empirical data. In this example epoch, both shuffled and real information increase with learning, and eye shuffle grows much faster than eye real. And that's also the case for the 2 epochs in monkey R. Again, monkey G oblique is outlier, So we did not observe any significant change of the real feature information. And if you remember the strange evolution of eye redundancy in this epoch, is primarily driven by the change in eye shuffle. So to summarize so far, I've showed you information redundancy increase with task learning, and it does not mean any impairment of population information, but reflects redistribution by generative Bayesian inference. So next, I'll move on to a much smaller time scale within a trial to unfold this inference process. So let's unfold the Bayesian model over time within a trial. On the first time point, the model forms a belief about orientation. And then this belief is fed back to sensory neurons at the next time point. You can say information in RT1 is carried over to RT2, and then so on. As a result, neurons will accumulate information within a trial, and since the information is shared and redundant between neurons, redundancy will increase as time elapses during the inference process. So we can confirm this prediction by our synthetic data. So we separate data into 8 different time bins and found information redundancy increased within a trial. And this is only true after the model learns the task, but not before learning. So again, let's see if our empirical data is consistent with the model. We also separated each trial into 8 time bins and computed the information redundancy within each time bin. So the solid line indicates late learning sessions. The redundancy increased within a trial starting from about 700 milliseconds. And as a comparison, the dashed line on the bottom is early learning sessions. Clearly, it does not increase. So the other task epoch from this monkey shows similar results, but with a different time profile. In oblique epoch of monkey R, we also observed a significant increase, but the increase happened very early on and then kind of plateaued. And for the other epoch, we did not see any significant change. So in summary, this result is clearly visible in 3 out of 4 epochs with various temporal profiles. So I'm happy to talk more about the epoch-to-epoch variability in Q&A session if you're interested. And lastly, we also confirmed that this increase of redundancy is primarily driven by a much faster increase of eye shuffle and not any decrease of real feature information. So far I've showed you our data support 2 predictions of the generative Bayesian model. And next, we want to look at how flexible information redistribution is. So if we change task context within an experiment session, and the change happens within tens of minutes or even seconds, can the redistribution process also flexibly switch, and how would that reflect in the information redundancy? So one advantage of the within session comparison is that it really speaks about the feedback connections. Because of biological constraint, the feed-forward pathway can change this fast. So the effect we see here should be contributed by the feedback signals. So first, I want to show you that changing engagement level can already alter this process. So after each task performing session, we also recorded passive viewing session, where the animals only look at the stimulus and did not need to make any reports. So we can compute information redundancy from those data and compare to the task data. In this example epoch, early in learning, information redundancy for both task performing and passive viewing are very low, and there's no difference between them. But late in learning, we can see redundancy during passive viewing is significantly lower than task performing. And this is true for the other epoch of this animal, as well as for one epoch of monkey R. So redundancy was higher when the animals were engaged with the task, which indicates that it has some flexibility and can change within a session. But the problem of passive viewing is that we have no control over what the animals were actually doing. So it is still possible that they were still engaged in some decision-making process, which could explain why passive viewing redundancy is very high in this monkey R oblique epoch. Another problem is that the animal performed the task for at least 2 hours, and then the passive viewing for half an hour. So the change of task context is pretty slow. So one approach to deal with this is to make animals switch between two tasks. Each of tasks has some requirements and constraints, and we can make the timescale of switching very fast. So because the task switching data has not been published and we are still working on the manuscript, I can only summarize the findings here and then give more details in the Q&A session. So overall, we found information redundancy also change with task context. So redundancy for cardinal task is higher under cardinal context and then the oblique context. But we did not observe any significant effect for the redundancy of the oblique task. And this asymmetry is consistent between two animals. Okay, so to summarize, our findings provide evidence in favor of the generative Bayesian inference. They suggest that the neural response in the mid-level visual area represent posterior distributions over some latent variable. Also, the feedback signals communicate prior and belief, which can introduce shared variability to neural response. But this additional variability is not necessarily harmful, but reflects information redistribution process by a generative Bayesian model, which the brain has built over learning. So any question about learning section before I move on to task switching?
Can you elaborate on the concept of information redistribution? What is it?
Yeah,
What?
so it's more like so how we have sensory neurons and then we have a decision-making area. So the decision-making area incorporates all the information from sensory neurons to form a task belief. And then this belief is fed back to sensory neurons. So it's more like this iterative back and forth information flow. So that's what we mean by information redistribution. And the result is like each sensory neuron carries information from the other neurons.
But then when you say earlier that the shuffled redundancy increase because information redistribution also happens for the unobserved neurons, you are talking
Ah,
about, yeah.
yeah. So it's like, so imagine this is like the whole, like all the task relevant neurons in the brain, and the distribution happens like within all of them, right? But we only observed of a part of the all the sensory neurons because that's how experiment, the constraint of experiment. Um, so so if you look at all the sensory neurons, like if you could sample all of them, then you shouldn't expect any increase of real facial information because like the computation itself cannot create any new information. Like the upper bound information is in the image. But the fact that we saw real facial information increase in our data is because we only look at a subsample. And this subsample has more information because they got all the information from the unobserved neurons.